Okay. Thank you for the introduction, and I thank for the organizers. So in this talk, I will talk about your probabilistic bijection from the 20 vertex model to almost one triangle. No, both kids don't react to uh, any. Working. Okay. So first of all, I show this number sequence. Why everything is broken? Sorry. Apparently every citation is broken somehow. I'm very sorry about that. Anyways, I have to continue. So I want to talk about this number sequence, which has appeared as the enumerations of several objects, such as Arrow-Gelfand string patterns, 20 vertex configurations, and domino tiling of the Aztec triangle. And the main question in my this research is, are there any combinatorial connection between these objects? As a sub-question, and which is also the question in this talk, is as follows: is there any combinatorial connection between 20 vertex configurations and the Arrow-Gelfand string patterns? And here is my answer. We construct a probabilistic bijection from 20 vertex configurations to the almost mono triangles, which appear in the -1 enumeration of Arrow-Gelfand string patterns. So I will explain these objects, combinatorial objects, soon. Before that, I have to introduce the probabilistic bijection definition. So now let X, Y be finite set with some weighting functions, Wx and Wy. Then also A is algebra. Typically, this will be, so in my talk, this will be as a set of real numbers. Then a probabilistic bijection from this tuple X, Wx to this pair Y, Wy is a pair of maps P and P bar satisfying the following definitions. So the first definition says so if you sum over all possibility, so you first fix small x in large X, then you take the sum over all the possible destinations from X to Y, then it sums up to 1. The second condition is now from large Y to X, then the same. The last condition says some reversible property. So now you have weight Wx, W large X of X times Pxy. Then this kind of like a weighted probability is same as P bar xy times Wy small y. So now our objectives are clear. Objective is to construct a probabilistic bijection from the 20 vertex configurations to almost monoton triangles, which are the objects. So again, I'm repeating the explanation, but which are the objects appearing in the -1 enumeration of Arrow-Gelfand string patterns. So time to introduce combinatorial objects of these probabilistic bijection. So first, 20 vertex configurations. So DiFrancesco already explained some about this vertex model, but the domain is now a little bit different. So instead of the square domain, we are studying this quadrangle domain. So there is a triangle tension below the square. Then we consider the uniform enumeration of the configurations of this domain. I'm so sorry. So So yeah, so it is known that the number of configurations is given by this product formula, which is nice. Okay, so this is the other community object. So this object already appeared in the talk by Uze. So I just skim that. So our get function pattern is basically a get function pattern with decorations on the entries. Then it has some properties which are not so important in my talk. Guys, example, maybe it's important to mention that. So this triangle carries some signs, and depending on what, depending on the number of special little triangle. So in this example, so special little triangles are colored by green here and here. Also, I have to measure that. Also, you have to count the number of this, like both arrow type of decoration in the pattern. This way, you define the -1 enumeration of allowed Dale function patterns. Then, it is known that this -1 enumeration is equal to certain weighted enumeration of Dale function patterns. With some constraints. Then this -1 enumeration gives almost the same product formula after this prefactor of 2 to some power of 2. So now I highlight the Dale-founded patterns appearing in this statement theorem. Actually, this pattern, these Dale-founded patterns appear as the like surviving set under some sign reversing involution. So almost monotone triangles is just so I just extract these Dale-founded patterns in the theorem, and I formulated it as a subset of Dale-founded patterns. I just extracted the properties the Dale-founded patterns should satisfy, which is here. Then weighting rule is the same as that which appeared in the theorem. So in this pattern, so 2 equal length. So for in each row, at most 2 equal entries can appear. And if this were at most 1 equal entry, then this were monotone triangle. But that constraint is slightly relaxed. That's why I gave this the name almost a monotone triangle. And here is the example. For example, in this row, there are 2 consecutive forces. That's why this is not a monotone triangle. Okay, so I finished introducing the combinatorial objects. So our next task is to construct the probabilistic bijection. So the probabilistic bijection consists of mainly 2 components, namely from 20 vertex model, from the 20 vertex model, by using the Yang-Baxter moves, you can construct the so-called mixed 6 vertex model. And by bijectivizing each Yang-Baxter move, you can define a local probabilistic map. And by composing those local probabilistic maps, you can define a whole probabilistic map from the set of 20 vertex configurations to mixed 6 vertex configurations. And from the the mixed six-vertex configurations to almost monotone triangles, you can define a certain price projection again. Then by composing these two probabilistic projections, you can get to the whole price projections from the 20 vertex configurations to almost monotone triangles. So that is an outline of the probabilistic projection. But due to the time constraints, I will only talk about the second part of the probabilistic projection, because the first part is just a translation of those Yang-Baxter transformation, which was done by the Francesco. So, okay, so here is the intermediate object of mixed six-vertex configurations, mixed six-vertex model, which has this rectangle shape. Then the boundary condition is basically the same as the domain of boundary condition, except that on the left boundary, the ingoing arrow and outgoing arrows are alternating. So that is the only difference. And so for each configuration of this model, I define the modified inversion number into the of x, which is defined as follows. So you look at the model, sorry, the configuration as a family of paths. Then you count these two patterns in the model. So you count the number of these local elbows in the model, but only for the even rows. Plus, you count the number of this horizontal local configuration in the odd rows of rows of X. Then we assume the rows are indexed from top to bottom. So it's one index from top to bottom, from bottom to top. Bottom to top, it doesn't matter because, in the end, the parity is what I wanted to explain here. And then here is a theorem. So the thing here is that, okay, so I explained this theorem one by one. This W omega is the evaluation, the weight of the mixed six-vertex configuration evaluated at the combinatorial point of 20 vertex model. So in the 20 vertex model, every configuration is evaluated to 1 at this combinatorial point. So that is the definition of combinatorial point. But for 20 mixed six-vertex configurations, the weighting, so how this weighting works for those computations is unclear. Actually, at least at first glance, it just looks like a product of some complex numbers. So that is what the hand side says. On the other hand, the right hand side shows some statistic which can be computed combinatorially. So that's the meaning of this theorem. So I show here an example. So a priori, this value, you have to compute this value by just multiply a lot of complex numbers. But instead of doing that, you can compute this number by counting these combinatorial patterns, so to speak. Okay, so the reason why I defined this combinatorial weighting rule for the mixed six-vertex configurations is that after this, I will translate each mixed six-vertex configurations to an almost monotone triangle in a combinatorial way, and I will show that it preserves the weighting. So to show that factor, it was more convenient to look at the commutative meaning of the mixed six vertex configurations, weightings, cause the commutative interpretation of mixed six vertex configurations can be translated into the intermediate object, which appears in the process of translating the mixed six vertex model to almost monotone triangle. So for each step, you can give the commutative interpretation with a weighting for that model. So the translation consists of several steps, that is 4 steps. So first, you interpret the path family as 1 minus 1 matrix as a usual way. So this corner gives entry 1, and this corner gives entry minus 1, and the other all the local computation give zeros. You get this matrix A. Then to this matrix, you calculate the partial row sum matrix from right to left. For example, about the first row, the first four entries are 0. After that, you have 1 here, you will 1 here, so 0 here. So for some remains 1, and so on. So this already appeared several times in this conference, I think. Then after that, you translate this zero matrix into a circular monotone triangle. So, and this map also appeared several times in this talk, but this time I just labeled the rows of the matrix in a slightly different way. Namely, I double the rows from bottom to top by 1 bar, 2 bar, blah blah blah, and k minus 1, k minus 1, k minus 1 bar, then k. But this is essentially just a normal monotone triangle. Then from this monotone triangle, the final step is just to forget all the bars in the triangle. So up to this point, every map was injective, but because of this forgetting operation, this map cycle is not injective. For example, for this monotone triangle, right? So from this monotone triangle, this entry 4 bar should have been 4 if you start it from a different mixed six vertex configuration, and that configuration gives the same almost triangle as this one. So that's why this is not injective. And then this is the weight preserving theorem I showed, meaning that so you take almost monotone triangle, then calculate its weight, then that you take all the mixed six vertex configurations and calculate the sum of their weights, then they coincide. Okay, so why? So this psi is a composition of the 4 steps I just showed. Then why this psi give a probabilistic is explained here. So from mixed six vertex configurations to monotone triangles, because from as I showed, the map is deterministic. So it's just a normal say map in the usual sense. So for each configuration, the destination is determined. On the other hand, when you are given almost monotone triangle, there are several possibilities which are mapped to that triangle. So I said this probability P bar according to the proportion with respect to the weight of the mixed six vertex configurations. Then for that this probabilities, these two maps P and P bar satisfy the conditions of a probabilistic bijection. So the first two conditions are obvious, pretty clear. For the third condition, to show the third condition, the theorem I just showed actually is needed. Then here is a conjecture. So so this is a generalization of the first theorem I showed. So the theorem stated a combinatorial interpretation of mixed six vertex configuration weights at the combinatorial point of the 20 vertex model. And in that statement, this head has 1, 2, 3, blah, 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 then up to n. So it was the most basic case boundary condition, but in this case, they can be arbitrarily strictly increasing sequence. Then this conjecture says that even in this case, if you evaluate the model, the mixed six vertex configuration as the combination point of the 20 vertex model, you can still get a certain combinatorial interpretation, which is actually the same. So the only difference is this three-factor part. There in which this large M is introduced. So large M is the maximum value level, which is independent of each configuration. So I stated it as a conjecture, but I already know how to prove this, but I have to verify my computations. So this is I'm 99% sure I can prove this, but because I did identify the discrete factor just yesterday, that's why this is still a conjecture. Okay, then if let's assume this conjecture true, then it will follow that the number of 20 vertex configurations where there are exactly n incoming edges and there are at most n plus 1 vertices on the left boundary. So you imagine that so at first its beginning I kind of fixed the left boundary condition with a 20 vertex model, but in this case only the number of incoming edges are bounded by n plus 1, and you consider the number of such configurations, then the number given by this product formula. So this is again, so this is due to the result by Isaac Fisher and Florian. There. Right. Okay. Okay, thank you for your attention.